Good. Okay, then let's start with today's lecture, which is on the RSA for domain hash. Let me briefly tell you what we are trying to do today. So last time we saw how we can construct secure digital signatures from one-way functions. And part of the construction was the hash then sign paradigm, where we took a hash function, a signature scheme for messages of fixed length, combined it with a hash function, and then we got a signature scheme for messages of arbitrary length. Now we want to look at RSA signatures. We already looked at those signatures a few lectures ago, and we saw that the textbook RSA signatures are insecure. The RSA function has this homomorphic property, and that is enough to already show that it's completely insecure. Nevertheless, RSA signatures in modified form are used in practice a lot. They are still probably the most popular signature schemes around. So the question obviously arises, why do people use these things, and how do they make sure that the insecurities, the weaknesses of RSA, textbook RSA, are not present in the signature schemes, RSA-based signature schemes that they use in practice. And in today's lecture, we will see one argument how we can actually combine RSA with hash functions to provide secure signature schemes. However, we cannot use our results from last week that showed that once we have a secure digital signature scheme, we can combine it with a collision-resistant hash function to achieve a secure digital signature scheme, because RSA is not secure. And then the question is, can we enhance the security of the hash functions so that the resulting construction, the combination with RSA, still leads to something that's secure? And we will see that an idealization of hash functions that is used quite a lot in modern cryptography can actually provide this security. And the idealization that we are going to use is the so-called random oracle model. It's used in quite a lot of constructions in cryptography, and it's often used to argue that certain constructions are secure, although this is usually not directly implied by the random or by the results using the random oracle model. So one has to take these things with a grain of salt. And let me first go back maybe to or define the random oracle model. The random oracle model provides a sound formalization for choosing a function from 0, 1 star to R, where R is some finite domain. You may think that we already have such a formalization because we already talked about random functions. But when we talked about random functions, we always talked about functions from a finite domain to a finite range. Here we have an infinite domain, and there is no notion of picking an element from the set of all functions from 0, 1 star to R uniformly at random, because this is an infinite domain. So we need to formalize it differently. The random oracle is one way to provide such an idealization. And it's actually an idealization and strengthening generalization of random functions, of one-way functions, of collision-resistant functions, and all kinds of other constructions. So it really is sort of, in a sense, stronger in terms of security than all these things that I mentioned. The drawback of this is that they cannot realize in practice. There is no realization in practice. One can actually prove that. So it's really an idealization. It's really something that we cannot construct, but we can reason about. And actually, as I said, this is done in theory quite a lot. In practice, and in particular, if you talk about signature schemes, what people often do is, well, if theoreticians talk about random oracles, the practitioners replace the random oracle by a collision-resistant hash function. And then they kind of assume that the security that we have shown using the random oracle also holds in the collision-resistant case, which formally is wrong. There's no argument why that should be true, and in fact there are cases where we can prove that this cannot happen, that this is not correct. But all these constructions are artificial constructions. There is, as far as I know, no real scheme that's used that has been shown in the random oracle model and then whose practical realization is not secure. You can construct these things artificially, but in general, this sort of works, and practitioners don't spend too many sleepless nights about this jumping from random oracle to collision-resistant hash functions. They just don't worry about it. Sometimes they often replace this by something that's stronger, but anyway. But this often leads to the interesting questions in practice, where we show the security of a construction using this so-called random oracle model, and then a theoretical, at least, but sometimes also practical question then is, can we realize the same thing in the standard model? Can we achieve the same properties using the standard model, where the standard model means we use a hash function or some similar construction that we really know how to construct in practice, that we really know exist at least under certain assumptions, whereas the random oracle doesn't exist in practice. So it's really an idealization. The random oracle is modeled by providing a so-called black box that for each new argument simply provides an image uniformly and independently at random. So here you want an argument or the image of a certain argument. You can go to your black box and that gives you a new image, uniformly at random chosen from R. That makes sense. Picking an element uniformly at random from R is a feasible operation because we assume always that R at least is finite. As a picture, we often view it as follows. So here we have this trusted party that sits inside a black box. And all participants playing, for example, a game or participating in a game in an experiment have access or can query this black box. So everybody participating in a game, for example, a security game, can send queries to this black box, to this trusted party. So here you see there are 3 different arrows going into this box, indicating that the queries come from different sources. And here one to h of x or for a different x. And so this query goes into this black box. Now the random oracle. Now the random oracle keeps a list of all queries that it has already received and answered. So it keeps a list of pairs xi, h of xi, where xi is a query that it received and the h of xi that it provided for that query. Now, if a new query comes, such an h of x, it checks whether there is already an x as a first component in this list of pairs. If so, it retrieves the second component of that pair and returns that y. This guarantees that queries are answered consistently. So if it always keeps a partial function. Partial meaning that defined on a certain number of arguments already. And if it's queried again on one of these arguments for which it already provided the answer, it returns the same y. If no xi exists with this x, no pair exists with this x as first component, then what the oracle does, it chooses a new y uniformly at random and adds the pair x comma y now to this list and returns y as an answer to the party that queried it. Okay? So that's the random oracle. Which means that if no party ever queried a value, then this value sort of is still completely random, completely unknown. Eventually it will get fixed by picking an element uniformly at random from this set R. Okay? But up to that point, it's undetermined and it can be anything. In particular, we have this property for this random oracle that if we have x1, say xl and xi is not equal to xj and x is not equal to xi for all these i's, then the probability of h of x being y, and we have also here y1 through yl, and we have a new y, conditioned on h of xi is yi, I from 1 up to l. This probability is 1 over the size of R. If this y was not queried. So at any point in time, for any x and y that was not queried, for any x that was not queried and any y from R, so the xi's are in 0, 1 star, and the yi's, y, r, and r. And this party inside of this box here behaves honestly. It will exactly do what it's supposed to do, what we describe in here. Okay. It's an idealization. I mean, in general, you don't have such a nice party, right? You don't have such a nice person that everybody can contact and ask for a random value on all these things and then keep track of all the things that have been already fixed. But as I said, it's an idealization. And you can easily see that if you have these things, this is a one-way function, it's collision resistant, it's all kinds of things. Okay. Good. Now we want to combine such a thing with RSA. Let me just briefly recall what RSA is, and then I talk about RSA generators. Okay? This is the same stuff that we already saw in lecture 7, I think. Yeah. So, or lecture 8 actually on the first part. So, as usual, by Zn we denote the ring of integers modulo n. Zn star denotes the unit group in Zn. So the set of all A in Zn such that the GCD of A and n is 1. This is true. You just need to talk about a representative for every class. If it's true for one representative, it's true for all representatives. And by phi of n, we denote the size of Zn star. And the observation is that A has a multiplicative inverse in Zn if and only if the GCD of A and n is 1, hence it sits in this unit group. Unit is the mathematical term for invertible elements. So all these elements in Zn star have an inverse. Now let's go back to this textbook RSA signature. We assume that for textbook RSA signatures there is a key generation algorithm that on input 1 to the n chooses two different primes of the same bit length, namely of bit length n. It sets n to be p times q. It sets, and then phi of n, as we can prove, is then p minus 1 times q minus 1. It chooses an e from z phi of n star, phi of n, not n, and sets d to be the multiplicative inverse of e modulo phi of n. As we just saw, this exists. And then the public key is set to be n comma e, and the secret key is set to n comma d. Signing a message with the secret key n comma d and a message from this space, this is somewhat arbitrary as I discussed in the previous lecture. We interpret m as an element in Zn. This here guarantees that it's a unique element in Zn, and outputs as signature the exponentiation of m with exponent d modulo n. Verification then on input 1 to the n and public key pk, L, which is n comma e, gets as input a message and a signature, and it outputs 1 if and only if we exponentiate the sigma with e, then we get m back modulo n. And that was the textbook RSA signature scheme, which was completely insecure because we know that with this definition, the signature on message m is simply 0, always. And hence we have found a forgery without actually using in our forgery game the ability to query for messages. But we can even also have the sign of plus 1 is 1, and also the signature of minus 1 is also minus 1. So and this actually, just to make sure, minus 1 here is the same as n minus 1, right? It's a representative class. It's in the same representative class as n minus 1. So this was completely insecure, and hence we cannot expect our theorem from last time that says if you combine a secured signature scheme with a collision-resistant hash function that you get a secure signature scheme. You cannot apply this here. This just doesn't satisfy the conditions of that theorem. Okay? So now we want to do this and combine this with a random oracle model. But we still have to make a few assumptions about this RSA signature scheme. And in particular, when we do this here, I did not specify how you pick, I did not specify how you pick these primes. Here, uniformly at random. Okay, here are specified a little bit. This is one way how to pick these things, but there may be many other things how to pick these things. Okay? And we want to abstract in our treatment of RSA from the specific way these things are done, but we want to make an assumption about these things and say, like, as long as your generator sticks to these assumptions, we will be fine. Okay? And that leads us to so-called RSA generators or secure RSA generators. So we call a PPT algorithm an RSA generator if on input 1 to the n, it simply computes two primes of length n. Whether they are uniformly at random from this set here, from this interval, I don't care at this point. And it sets then n to be pq and phi of n p minus 1 times q minus 1. That has fixed. It chooses e in z phi of n star in any way it likes. Specified by the generator of this algorithm. But then it has to set d to be e minus 1. And then it outputs this secret key public key pair. So for a generator, any algorithm that satisfies these things, we call it an RSA generator. But we do not specify how exactly it has to compute these primes or it has to compute this exponent e. Anything that does this is an RSA generator. But now we want to talk about good or bad RSA generators. And let me skip this one and go to the so-called secure RSA generators, or hard, that generates hard instances. So let gen be an RSA generator, and now we define relative to this algorithm. This is one fixed algorithm that sticks to the requirements of the previous definition. We define a game, namely the RSA inverting game, between a challenger and an adversary. And this game here is very much similar to the inverting game for one-way functions. And it goes as follows. So on common input 1 to the n, the challenger chooses the key pair n, e, n, d using the specific key generator, RSA generator that we are talking about. So this part here is determined by the key generator. Then y is picked uniformly at random from z to the n by the challenger, and the challenger gives n, e, the public key, and y to a. And a outputs eventually an x in Zn. And we say that a succeeds and the result of the game is 1 if x to the e is equal to y mod n. Okay? Otherwise, the result is 0. And we write RSA invert a comma gen of n is 1 if the output is 1. Okay? Now, here the question is, if you remember how I defined one-way functions, I always said we had a very similar game, right? Except that the function was fixed, so we didn't have this part here. But there I said, well, let's pick an x and then apply f to x. And then a had to provide a preimage of y under f. And I said we pick this x and then set y to be f of x because we want to make sure that a preimage exists. Okay? And do not ask the adversary to compute a preimage of an element that doesn't have preimages. So here I didn't do that. Right? And the question is, why didn't I do that? And the answer is that for each, and that follows from the things that we already discussed for RSA, if I pick an e in z phi of n star, then the function that goes from Zn to Zn and maps m to the e mod n is a bijection. Why is it a bijection? Well, we know that exponentiation with d is the inverse function. That was what we saw then when we proved that checking a valid signature with the corresponding secret key gives always 1. We saw that m to the e to the d is always m mod n. And if e is in z phi of n stars, then such a d exists, which e times d is 1 modulo phi of n. So this function here is a bijection, which means, if I go back to this game here, for any y, there is an x. And in fact, there is a single unique x such that this equation here is satisfied. So I don't have to don't have to make this detour of first computing x, then setting y to be x to the e, and then asking the adversary to find then this specific x, because that's the only x that's a preimage of my y. The other thing is that I want to mention here is this is not the same definition as one-way function, because in a one-way function the function was fixed, right? Whereas here, not in some sense, by picking this pair, this part here fixes a function, namely this function here. Right? And then you have to provide a pre-image for y under this function. And this y is chosen also from the corresponding domain. When we talk about trapdoor permutations, we will see this again. Actually, this will be one of our most important examples for trapdoor permutation. Okay. Now, when do we call a RSA generator gen a hard? Or when we call it a good one, it's a good one when the RSA problem is hard relative to this gen algorithm. And that means that for every probabilistic polynomial time A, there is a negligible function, mu, such that the success probability that A wins this RSA inverting game is a negligible function in N. So it should, a good key generator should output here things for which it's n comma e and y, in particular n comma e, for which it's hard to invert a random y. Okay. But it's the randomness that I have in here. The probability is over the complete randomness that's used in the game. And that randomness in particular includes the randomness and the definition of this key gen, of this algorithm gen. So to give you an example of a generator that's not good one is, if you go back here, can you, okay, maybe I asked it. Can you give me a generator that's not a good one, that for which the RSA problem is not hard, relative to which the RSA problem is not hard? Yeah? E to be 1. Yeah. So that he can even output good primes, right? Can uniformly at random, but if he outputs E to be 1, always, then because then this function here is the identity, and it's easy to invert the identity. Right? Similarly, if you would always output -1, and if you output +1 or -1 with probability 1/2, also not good. Or if you output E to be 1 with significant probability, always. All this is not allowed. Okay? But many people, for example, or it's even conjectured that a generator that picks primes carefully, let me go back here, that picks these primes carefully but chooses always E to be 3. That is often conjectured to be a good generator for which the RSA problem is hard. Okay? For if it always outputs 2, under certain conditions we can even kind of prove it if factoring is hard. But then, unfortunately, if you pick E to be 2, then this is no longer true. Then it's not a bijection, because 2 is not relatively prime to phi of n. Phi of n is p minus 1 times q minus 1. P and q are different, so at least one of them must be odd. and then phi of n is even. Okay? So there are lots of things that you can play around here. And we don't want to specify a specific generator. All I want to do is pick one for which this RSA problem, or relative to which this RSA inverting problem is hard. As I said, there are certain candidates, picking P and Q always the way we did it in our textbook RSA, and picking E to be E uniformly at random. That's a good candidate for one for which this RSA problem is hard, relative to which the RSA problem is hard. So that's a candidate. Okay, and now, so this is our assumption that we have to make about RSA. And then the next theorem shows that if we have a key generator that satisfies this definition, and then we combine textbook RSA with a random oracle or a function that's modeled by a random oracle, then we are on the safe side. We get a good signature scheme. So here is our construction. First of all, it's syntactically described, and then I will make a certain assumption, and then say, then it's a secure digital signature scheme. So let Gen be an RSA generator, anything that satisfies the definition 8.2. And let H, calligraphic H, be a set of functions, namely for every n in n. Say, just, it's sufficient if n is a product of two distinct primes, but never mind. For each n, we have a function from 0, 1 star to Zn. Publicly available means everybody knows, given n, what the function is. The RSA full domain hash with respect to Gen and H is the following signature scheme. The key generation algorithm is simply the key generation algorithm, it is simply the RSA generator. Okay? And the signature is simply hash then sign. So what we do with the textbook RSA scheme. So signature on input 1, n, d, the secret key, and m in 0, 1 star. It first maps m to hn of m, which is an element in Zn, so we can now do the exponentiation with d mod n. And on input n, e, m, sigma, the verification outputs 1 if and only if sigma to the e is the same as hn of m modulo n. So this is like hash then sign with textbook RSA and this family of functions. It's a little bit different than hash then sign, but it's mostly it's what we do. And it's a correct signature scheme. That follows from the correctness of RSA directly, because just replace what we had in the textbook RSA. We had the message in here, now we replace it by the hash value, but it plays the same role as in the textbook RSA scheme. Now, we would like to prove this to be secure, but we cannot use to our hash then sign theorem because RSA simply is not secure. Even if we have a good generator, the signature scheme is still not good. Okay? But what we can prove is the following theorem. If the RSA problem is hard relative to this generator that we picked for our construction, and if the functions hn in H are each of them modeled as random oracles, right, then the RSA full domain hash as in construction 8.4 is a secure digital signature scheme. So for this function hn, we have this nice third party that provides images as required to all parties involved. Right. Okay. And recall that if we talk about a secure digital signature scheme, we look at the signature forging game. And the signature forging game involves two parties, namely the challenger and the adversary. And both have access to this random oracle. And they get a consistent function or consistent view from the random oracle party. Okay. And always keep in mind this equation here, because that is the one that plays an important role. But we also need that the RSA generator is a good one. It provides difficult instances. Okay, so let's prove this theorem. And that's actually the only thing that's left for today. Okay, here's the proof. Okay, so what we do is exactly, yeah. Okay, so let A be a fixed but arbitrary, as usual, adversary against this RSA full domain hash with this key generator, with the RSA generator gen. Okay. Against in the game sign forge. So from A construct PPT adversary I against this key generation algorithm in game RSA invert. Oops, I called it A prime, sorry. A prime. And what we'll do, obviously, so if we show that, as I said already here, if A is PPT, we show that this is also PPT. And again, we relate the success probabilities in an appropriate way. Namely, if this one is negligible, then this one must be negligible as well. And then by our assumption on the RSA key generator that this is the RSA problem is hard relative to this gen, we know that this probability must be negligible. Hence, we know that our original one is negligible as well, proving the theorem. Then relate the success probabilities. appropriately. And we'll see how we can do that in this case. Okay? Yep. To make life a little bit easier, we make some simplifying assumptions that really are just simplifying assumptions, and they don't affect our generality up there. So let Qn be a polynomial such that for keys generated by gen on input 1 to the n, A makes at most q of n signature queries. Such a polynomial must exist because A is a PPT, so it cannot make more than polynomially many queries. Now we assume without and A, recall that we are talking about random oracle functions. So A can not only make queries to H, to the signature algorithm, it can at any point in time also query for a function, for the random oracle. It can always ask, please give me the hash value for some message. Huh? Because we are talking a random oracle model. Everybody has access to this random oracle, independent of signatures or whatever. You can just ask, okay, I want to see this hash value. So we have signature queries and we have hash queries. Yeah? We assume that A never makes the same query to H twice. So never makes this to the random oracle twice. Why should it do that? It gets always the same answer back. Right? So there's no need to do that. So if A does that, replace A by somebody who checks before whether he already queried it and just ignores this query. Doesn't change its success probability. Second, we assume that for any signature query on a message M, A has first queried this H, or Hn. I always drop this N here. Hn on input M first. That can only increase his success probability, because by querying H on M, it gets more information. Right? And getting more information cannot make you worse. Right? Unlike what many people believe, but anyway. Right? In this game, it cannot make your behavior worse. Okay? So we just assume that that's true. And if A outputs M comma sigma, we also assume that it had previously queried H of M. Again, if it did not do that, replace it by an adversary that does it. This can only increase his chances of getting a forgery out. Again, more information. So these are all things that instead of A's arbitrary but fixed, we may replace it by an adversary A that does this by simple modification, and the success probability of this guy is not worse. It is not better than this where we did this here, and when we can do this for anybody who follows or satisfies these assumptions, we are on the safe side. We have actually shown our previous. Okay? And it just makes life a little bit easier. To define, namely, in particular, this A prime against RSA, the RSA generator in RSA invert A gen. And here it is. Here is the algorithm A prime. So A prime gets as input 1 to the n, n comma e, and y, where n comma e is chosen using the RSA generator that we are talking about, and y has been picked uniformly at random from Zn, once n has been fixed. Yeah? Because that's the definition of our game here. Then we do the following. We simulate A with input pk as n comma e. And says again, I dropped the n's here, the subscript n in all h's here. And in a table T, A prime stores triples mi sigma I yi, where h of mi is yi. This is the information you will get from the random oracle. And we will also have that sigma I to the e is equal to yi. How we do that, we'll see. And before that, we also picked this index from 1 through q of n. Remember, q is the polynomial that limits the number of queries that A asks. Okay. So we now do the following. And recall that before A makes a signature query on a message, it always has asked the random oracle for the hash value on that query. But anyway, so we now have to say, how do we answer A's queries? So when A makes its ith random oracle query h of mi, it can always do that. We do the following. If j is equal to I, we return y. Okay? If the ith index is this j that we picked here before, we simply return y, period. Otherwise, so I is not this index j, we choose sigma I to be Zn, from Zn, uniformly at random, and we set yi to be sigma I to the e, and we return yi. Okay? So we do not simply pick an element yi uniformly at random from Zn. We compute it in this way here. Okay? And I will say something about this in a minute. Okay? Just for the time being, just take it as I defined it here. Then when A makes a signature query for message m is equal to mi, if y is not equal to j, hence we have, and recall, when I ask for a signature query, A prime, or A asks for a signature query, it has already asked for the hash query. It has already asked the hash query. So then T contains such a triple already, right? Because this hash query has been done. So it contains a triple mi sigma I yi. And it returns sigma I, sorry. It returns sigma I. Otherwise, we abort. If it's I is equal to j, we abort. So we cannot answer and do not answer queries for this particular index. And if A outputs m comma sigma, we output sigma. Okay. So what is this thing trying to do? Recall that we assume that if A outputs m comma sigma, it has queried h of m. So what we hope is here is that the jth query to the random oracle is in fact on the message for which it will provide the forgery. Okay? We know that there is some index for which the eventual forgery message is the hash query, and we hope that it's the jth one. Okay? Yeah? Now we can two observations. So, or observation 1 is for all I in 1 up to q of n, the random oracle queries or hash queries are answered as in game SignForge, i.e. by choosing elements uniformly at random. The proof, again, recall that we assume that A never queries the random oracle on the same message twice. So they are all different. So for this query here, that this follows for y, this follows from definition of RSA invert game. Why? Because, well, in the RSA invert game, where is it? Oops. Here it is. Y is picked uniformly at random. No? Okay. No? Now what about the other queries? For ith query, I is not equal to j. This follows from lemma 8.2. Oops, where is my lemma? Lemma 8.2 says that exponentiating with E is a bijection, right? So instead of picking an element uniformly at random directly from Zn, I can also pick an element uniformly at random and then apply the bijection, right? Because on a finite domain, a bijection keeps the uniformity. Everyone has a single preimage. Okay, and that's exactly what is done here. I pick an element uniformly at random, and then I apply a bijection. So this is also uniform at random. That's again why that this is a bijection. So this claim follows from this. Next, observe that if we guess this index correctly, then we answer all signature queries correctly. Because then the sigma E is exactly what we want, right? If you do, this is exactly the right signature. Because then we have to make sure that this h of m, where we have this equation with h of m. So let me erase this. So the second observation is for all I not equal to j, signature queries are answered correctly. Proof. Why is this so? So we'll have to go back to the definition of our scheme, right? Here it is. We know that, so by definition, for I is not equal to j, we have the triples mi, sigma I, yi satisfies, first of all, that if you go back here, we have that h of mi is yi, right? That's how we defined it. And hence h of mi to the d is yi to the d, which is sigma I to the e to the d, which is sigma I to the e times d. And that is by our textbook RSA stuff, this is sigma I mod n. Right? And this is exactly, sorry. Yeah, no, that was too complicated actually. It's true, but it was too complicated. We have to check that this is true, right? But this is by definition, right? By definition of yi comma sigma I, we have h of mi, which is yi, which is sigma I to the e mod n. This is the way we constructed these things. So at these points here, we were cheating. We were cheating in answering these queries by first finding the signature, then exponentiating it so that we get the right thing to answer for the hash value. And this worked because raising things to the eth power is a bijection, so that the distribution is correct. Sigma to the e. Except, of course, when we come to this query here, then we need to compute a pre-image for y. We needed to compute a sigma such that sigma to the e is y. We don't know that. Okay? But if that is our forgery, then we really get a pre-image for y, which is exactly the task that we have to solve as an RSA inverter. So now we can conclude the proof, basically. So denote by J star, the random variable for the choice in step 1 of A prime. That is the probability for all I, the probability that J star is equal to I is 1 over Q of n. Just to make things formally correct. Yeah. And now we want to analyze this probability that A prime wins. Yeah? So we want to look at RSA, invert, and we call this RSA gen, the thing that we have, right? So RSA A prime against RSA gen on input n is 1. Yeah? Yeah? And so what we can say is that this, by what I said is this is at least the probability that simulated A outputs forgery and J prime is equal to J, where J is the index that we pick here. Or let's say, yeah. Yeah. Good. Okay. But this, we use our usual stuff. We do conditional probability. This is the probability simulated A output forgery. Conditioned on J star being J times the probability for J star being J. Now this we know is 1 over Q to the n, picking it uniformly at random. Okay. Now this here, conditioned that we pick the right thing, right? By which I mean that, okay, where J, sorry, I forgot this here, where J is the cache query for message M and A simulated A outputs M comma sigma. So J is the query, is the index for the hash query for the message that A outputs as a forgery. Again, we know that such an index exists. Since such an index exists, we know that this J star in the first is this with 1 over Q to the n. And we also know that if we pick that index correctly, then we answer the hash queries correctly, and is as in the inverting game, as in the forgery game, and we answer all signature queries correctly, as in the forgery game. So in that case, so conditioned on this, this is the probability of sign forge A against RSA full domain hash n is 1. Okay. Or in other words, this one here, this probability here, is upper bounded by this probability times Q of n. We know that this is negligible by our assumption on the RSA key generator that we are using. Negligible times polynomial is negligible, which shows that this here is negligible for all a's. And we are done. Okay. And that's it already. So what we did here is a general technique that's used in almost any proof using the random oracle, is we program the random oracle. We program the random oracle in such a way that the answers are computed correctly, in the sense with the right distribution, but we do know something about them. Right? And these two things do not exclude each other, as you can see here. I can answer them correctly, namely the uniform distribution, but I program them, or prepare them in such a way that I know always a pre-image under this exponentiation with e. Okay? Okay? So that's kind of funny, right? You would think that, well, uniformly at random is uniformly at random. No. I can do it in such a way that I know a pre-image under a bijection for it, because I just computed in the other direction. Right? And that allows me to answer these things. So that's what's called programming a hash function. And then this is, as you can see, is a version of bit guessing, obviously, right? The technique that we used, that we call bit guessing. So it's a combination of two important techniques. It's a combination of bit guessing, or three techniques, random oracle, overarching theme here, and then we use programming the hash function. And that gives us this result that RSA full domain hash is secure if the RSA generator is a good one, namely the RSA inverting problem is hard relative to this thing, to this generator. Okay. And that, as I said, is so in practice, RSA signatures often are mostly are, take textbook RSA, take a collision-resistant hash function like SHA-3, SHA-2, do that, period. But be aware, this construction is not shown to be secure using this proof, because SHA-2, SHA-3 are not random oracles. But in practice, we don't know how to exploit that to prove these things insecure. Okay. Questions about this construction proof? If not, then Thursday is a holiday, so don't get up at 7 in the morning hoping for a lecture. There will be no lecture. But the week after that, there is a lecture, and then we look at hash functions in more detail. Collision-resistant hash functions and also universal one-way hash functions that can be constructed from one-way functions that are good enough to secure one-time signatures with arbitrary message length. Okay, then that's it already for today. Thank you.